Hi, and welcome to this presentation for the 2021 GNC Conference. Today I will present to you the mission and GNC system design of Juventas. Juventas is one of the two CubeSats in the HERA mission, and it is being developed by ComSpace Luxembourg. GNV has the responsibility on the onboard guidance navigation and control system. The main objective of Juventas is to study the internal structure of DIDYMOS, the smallest body in the DIDYMOS asteroid system. Juventas will face a highly uncertain environment in which the solar radiation pressure perturbation at the working distances of Juventas is comparable to the gravitational pull of the secondary body. And this will become important for the mission design, as I will explain later. To fly in such a highly uncertain environment, Juventas carries many sensors, among which we can find two intersatellite link antennas used for communication and also for orbit reconstruction on ground. There is also a visible antenna and a laser altimeter that will be used by the guidance navigation and control system. There are also one star tracker, two IMUs, sun sensors and infrared sensors. Juventas will face its main payloads towards the asteroids, and the GNC system will be in charge of commanding this attitude. Juventas, as I said earlier, is part of the HERA mission, and it will be released from the HERA spacecraft. Since the release, Juventas will be inserted in a set of hyperbolic arcs until it arrives to the final destination orbit, from which the scientific measurements will be taken. Since release until it is injected, a period of 2 weeks of dedicated operations are foreseen. The design of this mission is quite important since there are many constraints on the possible directions in which Juventas can be released, and also operational constraints to ensure the proper commissioning of Juventas, and also that the communications are always ensured between HERA and the CubeSat. Once Juventas arrives to its final destination orbit, it will be inserted into a really specific type of orbit that only exist in environments where the low mass of the bodies produce a gravitational pull comparable to the solar radiation pressure perturbation, as I said earlier. These orbits have the particularity that Juventas will stay in a predictable and bounded distances to the asteroid, and the solar radiation pressure perturbation will be in charge of keeping Juventas in these almost circular orbits, thus ensuring that a low maintenance is needed for the mission. Then, from these orbits, the low-frequency radar, the main payload of Juventas, will be imaging DIDYMOS. Once this is completed, Juventas will try to land on the surface of DIDYMOS. Juventas will place itself into a collision course trajectory, and thanks to the GNC system that will be executing maneuvers to ensure and maximize the chances of a successful touchdown on the asteroid, Juventas will be able to use its second payload, a gravimeter, to measure the dynamical environment around DIDYMOS. The GNC system is a software module running on board the onboard computer of Juventas. It is composed of mainly two modules: the GNC system itself, that carries all the functionalities of the guidance navigation and control, and the image processing, in charge of of processing the images taken by the navigation camera. The GNC system will communicate with other software modules of Juventas through a protocol called CSP. As I said earlier, the IP system or image processing will be in charge of processing the images taken by the navigation camera. The IP will use two algorithms depending on the target body. For the DIDYMOS, maximum correlation with a Lambertian sphere is used since it has been assessed and proven a robust approach to compute the line of sight from Juventas to the asteroid. However, for the last phase, on the landing, where the navigation camera will be pointed towards Dimorphos, another algorithm will be used, a center of brightness, simpler algorithm but more robust, and this is a decision motivated by the lack of knowledge on the shape of Dimorphos. The GNC has many modules, such as a fall detection and isolation system, a mode manager in charge of commanding the different modules in the different situations that Juventas will follow, the orbit determination and control system composed of a navigation filter, and the attitude and translational guidance. The translational guidance is based on a fixed time of arrival. It will be used to command translational maneuvers during the landing that will ensure that Juventas finds its trajectory towards Dimorphos. Then the translation of a navigation system consists on an extended Kalman filter that will process the output of the image processing block and the measurements coming from the laser altimeter to compute the state of Juventas with respect to the asteroid. Then using this state, Juventas will command to the ADCS system an attitude to point the navigation camera towards the asteroid. This navigation system, this attitude guidance subsystem has many autonomy levels, and as I will explain in the following slide. The GNC mode manager is in charge of commanding the different modules and model operations of Juventas in the different situations that CubeSat will encounter. For instance, during safe and any other contingency scenarios, the GNC will be in standby mode, waiting for reinitialization. In nominal operations, these are when Jura will be taking measurements of the internal structure of Dimorphos. The GNC will command the attitude of Juventas towards the asteroid. This can be directly commanded by ground, corrected by the GNC, or fully commanded by the GNC system. During propulsion maneuvers, the image processing will be deactivated, and during the landing, the translational navigation will be activated to command the translational maneuvers. Then the GNC FDAR system will be also in charge of ensuring that all the inputs used by the GNC and also the outputs are okay, and try to detect and isolate any possible contingencies. The GNC uses an incremental development process in which several test beds are developed along the development of the GNC itself. The GNC is being designed and developed in MATLAB Simulink in an environment called GNC FES, Functional Engineering Simulator, that I will explain later. Later, these models are auto-coded into a final flight code that it is integrated and tested in a software testbed with a representative model of the onboard processor of Juventas. And later, the GNC will be tested with real hardware in the avionics test bed. For the development of the GNC, the Juventas Functional Engineering Simulator has been developed. In this simulator, the models of the GNC are designed and tested against models of the real world itself, and also all the onboard processes with which the GNC will interact. These are the ADCS, Attitude Determination and Control System, and the command and data handling processes. In this environment, the first part of the validation of the GNC has been performed, and these are the model in the loop test campaign. In this presentation, I will show you the results for the two main phases of the Juventas mission, the two most important parts of the mission. The sun-stabilized terminator orbit at 3.3 kilometers, from which Juventas will take its scientific measurements, and also the landing. Monte Carlo campaign using the GNC in closed loop simulations in the FES has been performed, and it has been observed that the GNC system is able to compute the state of Juventas with respect to the asteroid, and safely command the attitude of the body of the spacecraft with respect to the body, with an error of less than 1 degree in all three axes. During the landing, Juventas is inserted into a collision course trajectory commanded by ground, and then Juventas has to first estimate its state and command two maneuvers to correct for its dispersion, and to carry Juventas back to its nominal trajectory to maximize the chances of a final landing. 50 meters, when Juventas reaches 50 meters above the surface of DIDYMOS, a braking maneuver will be executed. This has the purpose of ensuring that the final velocity is perpendicular to the surface, and also small enough that after the first bounce, Juventas does not escape back into the deep space. Then, once this braking maneuver is executed, the GNC system is switched off in order not to interfere with several bounces that Juventas will perform on the surface of DIDYMOS until it rests on its surface. During this phase, the navigation camera will be pointed towards DIDYMOS, and up to a point the asteroid will be larger than the field of view of the camera. Then the GNC system will stop using optical images, and it will rely only on altimetry. And this will ensure that that the final destination and touchdown is reached, and Juventas can successfully finish the mission. That has been all I wanted to present today for you, but I would like to know if you had any further questions, and I would gladly answer all of them. So thank you very much, and I hope you have enjoyed this presentation.